Alright, so hello and welcome. Guten Abend, good day, howdy, hello. We have another problem to work on today. Coin change 2, and I've already looked at this problem. I actually already solved it. I thought this was a really interesting problem. I think the other day we said we were going to look into here, let's go to normal. So the other day I said I was going to look into palindromic sequence subsequences. We were going to probably look at the discussion, but I came up with a solution to this problem, this coin change problem, and I already wrote it. Surprise is ruined. All right, yeah, I didn't actually run it though, but I'll rewrite it again. I'll explain. This is a really interesting question, or at least a really interesting question, interesting solution. So. I will explain. Also, is that all you need in your? Anyway, yeah. This is a super interesting question. I'll read the question and try to explain the solution. It's gonna take me a while to explain it though, but like it's so succinct and it's so good, it's so perfect, it's great. So here, let's explain it. We'll read it. You're given an integer array coins representing coins of different denominations and an integer amount representing a total amount of money. That return the number of combinations that make up that amount. If that amount of money cannot be made up by any combination of the coins, return 0. You may assume that you have an infinite number of each kind of coin. Answer is guaranteed to fit into a assigned 32-bit integer. This is kind of a classic question, right? So if you had if you can imagine a dollar, like how many ways can you make up a dollar? In terms of cents using coins, right? That's like a classic question. And then this is like if you had arbitrary coin numbers to work with, how would you do it? So the solution goes like this. First things first. So the deal is, this is very similar, by the way, to the subset sum question, where let's say you had a set of numbers, and there could be duplicates or just an array of numbers. It could be duplicates, and you could only pick one at a time, and you want to know whether or not, or even not even just whether or not, but how many ways can you add these numbers together into a subset sum to get a certain target number, right? This is very similar to that, where in that problem, which we've actually looked at a few times now, in that problem, you can only use each selection once. In this problem, there are no duplicates because you can use your selection as many times as you want. But what's really interesting about this problem is that the two different solutions, there's two dynamic programming solutions to both of these problems that they're like mirror images of each other. They're so similar, and they're really interesting, and they're really quick to write. So I'll explain this one. The explanation for that one, I guess I tried to explain in another video. I didn't really see it, didn't really understand it. This video I can actually explain, because I came up with it using that as an idea. Because I was like, well, if they're different from each other, how are they different? Why are they different? And like, how different are they? So the solution to this problem, at first I thought was, hey, let's write a recursive approach where we would say, and memoize it and say, add together all of the different ways. So if we have like some amount x, and we have coins 1, 2, and 5, right? X and 1, 2, and 5. Add all the ways that you can do x minus 1, x minus 2, and x minus 5 with those coins. Add that all together, and that'll be, and we'll get a number there. And as it turns out, that's not correct to do it that way. And I tried to optimize that. I tried that approach. And I thought, okay, well, why is that wrong? Right? Why is it the wrong approach? And the reason it's wrong is that you'll end up with duplicate values, right? And I thought, well, you could maybe write this in such a way where you can handle the duplicate values. And you probably could do that, potentially. However, that's not the best way to do it, and it's not necessarily what they're asking for. It actually might be kind of too slow, believe it or not, if you did that. That might actually be too slow with these bounds. So I said, okay, well, what's wrong then? Like, what's like a better way to do this where I don't need to get rid of these duplicates? And I said, all right, let's try like doing one coin at a time, or removing one coin at a time, or not using one coin. So like if we had all the different, so we had just two coins, like dimes and nickels, right? 10 sets of values of face value of 10 and a face value of 5. If you had 100, you would say, okay, I can use 0 dimes, 1 dime, 2 dimes, 3 dimes, etc., all the way up to 10 dimes, and then whatever's left over, since I'm already considering all of the dimes, whatever's left over, I can now compute with just the nickels, right? And so you would say, so from there you would say, basically that creates a partition, right? It's a sum over a partition. You can partition on the divisors, the multiples of the dimes, and then the nickels. You can actually you can solve that directly, right? That's actually straightforward. Is that everything that has is a multiple of 5? It's a 1, right? It only has one possible way to create it, and then everything that isn't a multiple of 5 has 0 ways. So the nickels you can find directly, and then the dimes you can partition based off of how many dimes you are using, and then each of those, you add all those together, but each of those you could multiply by the number of ways that you can get whatever's left in multiples of 5. So that got me thinking, and then you add all that together, and that got me thinking. I thought, wait a minute. This sort of creates like an inductive approach where you can do the same thing now with if you had another coin, let's say a quarter, right, 25s, where you can partition again based on 0 through 4 if we were using 100 quarters, and then add for each of those possibilities what we had just calculated for using two other coins, right? And what's interesting about this is that the solution for, let's say, if you used 7 dimes, right? The solution for 7 dimes would be calculating for 30, right? 30 with something you've already calculated, with a pre-calculated value, and you're going to add that to your total, but that's also going to be, how do I express it? Like, if we just consider dimes and nickels, what you end up with is if you used so if we brute forced this approach, we used this approach, we brute forced it, and we calculated for every coin, we calculated, and every from this value, right? So from this amount, we're going to calculate a matrix, I guess it could be a matrix. Every value that's less than that amount, and whether or not it's and how many ways you can get there with one coin, and then we use that result and calculate again with 2 coins. That means that each of those numbers, for each of those numbers, you need to sum all the different ways, all of the intermediary steps, right? So for 100, it's f of 10, f of 20, f of 30, f of 40, f of 50, etc. Or really 100 minus that value is you have to look up in the previous table and add those all together, and then that's our new f of 100. So maybe that's the way to express it. So the new f of 100 would be the previous f of 0 plus f of 10 plus f of 20, etc., all the way to actually it goes up to 90. I think you don't actually add there is no f of 100 because it's actually 100 minus the number of dimes you're using. So, well, if you use 0 dimes, yeah, well, f of 1, and f of 100 is already what we just computed. So actually, yeah, you add the previous f of 0, f of 20, f of 10, f of 20, all the way up to actually the previous f of 100, right? You sum all those up. So that algorithm would take quadratic time in the amount, roughly quadratic, and multiplied by linear in the coins, because we're doing it for each coin, and we're doing it roughly O of the amount. We're doing it definitely one routine for the whole amount, and we're also doing roughly the amount divided by the coin size, which is bounded by the amount. So obviously, if we're using relatively small coins, it becomes basically quadratic in the amount times linear in the number of coins. Okay, now here's what's interesting about that. If you think about it carefully, you realize a few things. Also, we're like 11 minutes in the explanation. This is, yeah, I was kind of, this could be like a 5-second video. I just typed out the solution and hit submit, and that was it. But what's interesting is, if you think carefully about the solution, first, you don't need a matrix of data. You don't need that much memory. You only need the previous vector, right? You only need the previous f of x, we'll call it. Excuse me. And you're calculating a sum over that previous f of x for the new f of x. But if you think carefully, pay attention carefully, you'll realize that these values that you're calculating are summations, are cumulative values. And in fact, you don't actually necessarily need to go over all of the previous cumulative values. You may only, if you store the previous cumulative value, in other words, if you calculate the previous cumulative values before you calculate the value you're going to calculate now, you actually don't need to add all of those values again. You're actually doing redundant work. So you can actually do the new f of 100 is equal to the previous f of 100 plus the new f of 90, because the new f of 90 is equal to, is sort of recursively equal to that sum that we were looking for. Which means that you can do the same solution, which means that actually you can do the same solution for the subset sum problem if you just reverse the direction of the array, of the dynamic array, and I'll show you what this looks like. So this is super interesting, and I'm fairly certain this works. I don't really have like a formal proof, but I think it's correct. So you can do amount plus 1 and 0, and you can say, and we're going to use DP instead of V. So dynamic programming, and we're going to say for int x in coins. I'm going to say for int I equals, start off at x, I is less than or equal to the amount, plus I, and say dp of I is going to be dp, is going to be plus equal to dp of I minus x. And so if you go this direction, and the other solution, by the way, and then you take return dp of amount. And the other solution, by the way, this loop is inverted. Basically, you go from the top to the bottom, and you only add a value once. Whereas this approach, you add the other values any number of times, basically every number of times that's possible. And so we can throw in some test cases here. So we have 3 and 2. We have 10 and 10. We have 100, 1, 2, 3, 4, 5, 6. We have 0 and 20, and we have I don't know, 1,000 and 500 to 25 and 2,000, 2,000 and I don't know, something else, 2 or 20, something like this, some random stuff. Let's see if we've got the right idea. Wrong answer. Oh, I made one mistake, which is the initial dp of 0 has to be set to 1. I forgot. That's the only thing you need. You need to initialize with there is. You can, yeah, obviously if you just add zeros all day long, you won't get the right answer. There is one way to get nothing, and that's with no coins, right? With no coins, that's one way to get 0. So d of 0 is always at least 1. Let's see if we get the right answer. Yeah. It's interesting, we do get 0 for the first one, 3 and 2. Yeah, there's no way to get 3 with 2, right? So I think this is correct. We're going to go for it. Let's see how we do. Hey, got there. Sweet. This is about as fast as I can do it, too, I think. I mean, this is like about as good as it gets. I really don't know of a better way to do this. It's really, really succinct, really efficient. My opinion, kind of impressive, actually. I'm impressed. I impressed myself with this. I figured this out earlier on my own, and I was like, hey. Too bad I'm not 100% though. I don't know. How can you do it faster than this though? Like, oh, I know how to do it faster. I got it. Oh no, actually, never mind. That won't work. No, never mind. I was gonna say you can do a what do they call that array? Just a regular array of this size. That might be a little bit faster than the vector, but I don't think it'll be that much faster. Maybe there's something to do with this loop to make it faster. I don't know. That's about as good as I got. As good as I could think of. Maybe I just got to keep hitting the submit button until I get the fast until 4 milliseconds or something, or to 0 milliseconds. I don't know. I don't know how to do this faster. There's got to be a way to go faster. No. I'll wait a few more seconds. I'm actually kind of disappointed that this isn't like extremely fast. Really, how do you go faster than this? Is it the array access maybe? Maybe you gotta use iterators. Maybe that's what we need to do instead of doing the array accesses. Maybe you can even optimize this part. I don't think so. That's probably about as fast as it gets. Try one more time. How are we doing on time? 17 minutes, 20 minutes. Yeah, not too bad. Yeah, I think I'm gonna go. I think I'll stop there. I'm satisfied. That's pretty good. That's pretty good. It's not 100%. I don't know how we're not 100%. That's probably about as well as you can do it, but that's okay. All right. So thank you for watching, and I'll talk to you soon. Yeah, we'll get into the next one, which is the longest increasing palindromic subsequence. Is that what it is? Longest palindromic subsequence. We'll get back to that in just a moment.